Let's look at the example for the BFS. In the DFS, if we still remember the DFS, we have two kind of edges. When we discover the edge, we call discovery edge, and we call back edge. The back edge means we return back to the node that has been visited. But for this BFS, so this is BFS. In the BFS, we have discovery edge and cross. So what is cross edge? Based on what we saw on the pseudocode, we can find what is cross edge, but let's see in detail about this one. So at the first, we have L0. What is L0? This is the level. Okay, we call it L as the width of level. In the level 0, it is the initial where the starting node. So let's assume that we start from A. So A will be the node in the L0. And then now let's look at what are the incident edges of. So the incident edges of A is this one. And then we have another. So the connection between A and B, because we have one here, we put B as a node in the L1, or this is the level. Then we will check this one as visited product, and we will check this B as visited product. And this X is D. This is the discovery X. And the other node has not been. Next, I will check the other incident item from the L0. So the L0 is A, and then I would like to explore in the L1. In the L1, I have B. This is the incident F. And then I have another incident F from here, which is going to C. And then I will have another incident F, which is going to D. But we'll check this one. Now, the next we'll check the incident F. Because C is unexplored. And then this X is also unexplored. And C will be noted as B, or this is the visited product. And then we have the AD as D of discovery. And then we go to that. We have A, B, and then A, C. So we also still have another hidden. Then we'll check. Is D unexplored? Yeah. Then we can go to D. Then we put this as visited product. And this E is also unexplored. Then we put this as discovery. After we finish with the L1, okay, we call this is the L1, we can explore the other. Now we will check from B. Okay, we finished with the L0. So we can go to B. Now in B, we can look at this F. What is F? This is the incident F from B to another. However, what is C? C is already visited. Because C is already visited, then we will use this X, which is from B to C as the cross. So this is the cross. It means the X which is in the same level, or the X which is going to another node that has been visited, we can denote it as cross. So is already visited, then this is cross. The next, we will explore from B and check what is the incident S from B. The incident S from B is E. So E is E visited, because E has not been visited, then E, well, we go to E, so E will be noted as visited. And then B, E, the node, sorry, the F will be a discovery. And then we will go to the next, which is C. C is a node, and there is an incident X. The incident X of C is this one, and it is going to D. What is D? D is a node that has been visited. Okay, because D is already visited previously, then this X will be considered as profit. And then next, we will check the incident X of C. The incident X of C, okay, this one. If we go to E, E has been visited. Because E has been visited, then it will be cross. So C will be cross. We can explore the next, which is the incident F from C to F. F has not been visited previously. So F has not been visited. Then we note F as visited. So CF will be discovery. The last note we will check from D. So from D, we need to check what is the incident F. So there is an incident F here, and the incident F here is going to F. F has been visited. Because F has been visited, then DF will be the cross. So we can have this kind of thing. If every node has been visited, we can explore what are the status of D. So this is the status for of D. So in the DFS, we have properties. In the BFS, we also have properties. So GS means a connected component of, and the property one means that the BFS visit all the vertices and edges of GS. So if the graph has a connected component of S, then we need to visit all vertices and all edges. The discovery edges labeled by BFS G, S. So if we can discover this one, okay, so we will label it from the function BFS G, S, and this will be the final tree. Is the number final tree. So the result of DFS and BFS will be final tree. The property tree. So when we have the vertex V in Li, L means the level. The L0 is the starting node. L1 is the next level after the starting node. And L2 is another level after the L1. For every vertex in the Li, the path from Ts from S to V has I edges. The path from Ts is this one. This is the starting point. From S, so let's say this is S, to V, to V. So if it is in the L1, so I equals to 1, then there is an X from S to V, there is 1. So one more time. The path from Ts, it is from the tree, starting from S to V, there will be I. I is 1, so there will be 1. How about if I go from L0 to L2? So there will be 2F and so on. So if we have L3, then there will be 3 edges from F. If we have L4, then there will be 4 edges from F. Every path from S to V in GS has at least I at least. This is the minimum. So the analysis for the algorithm, okay, we can look at the set and get of the vertex and edge label. It is O1 time. Each vertex is labeled twice, the same with BFS. The first is unexplored, and once we visited the edge, the vertex, we would visit it. Each edge is labeled twice. The first time we will label unexplored, and the other we will label discovery or cross. So discovery means it is an edge where the opposite node has not been visited. Okay. The cross edge means it is an edge where the opposite node has been visited. Okay. Each vertex is inserted once into the sequence L. So once you visit a vertex, it will be inserted one time in L. Method incident edges is called once for every vertex. So if a vertex is visited, then you will call at least one time. So the BFS will run On plus M. It is provided that the graph is represented by the adjacent. So if then the BFS run at its big O notation. So recall that the summation of the degree V equals to 2M. So there are some application. Of course, we can use the BFS and DFS on the same problem. So using the template method pattern, it means we can use the BFS G, comma S, or S can be any vertex. We can specialize the BFS graph version of graph to solve the following problem in On plus M. So compute the connected component of G. So I want to know whether the G is connected or I want to find a G, whether the G is a spanning point. I can also use the BFS to find simple cycle. So BFS can be used to find cycle. Or we can also find whether G is the point. And also we can use BFS to find given two vertices, find a path in G between them with the minimum number of edges. So if I have a graph like this one, so let's say I have this one. So I can try to use BFS to find a path. Okay. So we want to find a path between U and B with the minimum number of edges. So if I go from U to here, 1, 2, 3. So if I go from here, 1, 2, 3, 4, 5. We need 5 edges. If I go from here, 1, 2, 3, 4, 5, 6. 5 edges. Then here you need 5. Here you need 4. And from this path you need 3. So you can select, let's say this is the minimum number. Go from U to B through this path. So that's also the application of BFS. Yeah, in the theoretical, in the literature, they mentioned that some of the application of BFS are intersection. For example, you can find the spanning point. You can check the connected component. You can find path. You can find cycle. For the BFS, it is good for finding the surface. For BFS, it is good to find by connected component. But actually, you can use BFS for surface path, but the BFS will be better. If you use BFS for by connected component, that is also good, but BFS is better. So the difference between DFS and BFS. When you use DFS, you need to check the back. What is back edge? W is an ancestor of B. You still remember ancestor? So if we have a tree like this, so this is the child, this is the parent. If it is the parent, then we go, this is the ancestor. So once we know that W is the ancestor, then it is like cross F. Cross F in the BFS means the W is in the same level of B. So this is L1. So the B and C and D, they are in the same level. Or in the next level, for example, E and F. Okay, so we can have this is a cross F. We can have also this is the cross F, where E and F is in the next level. So that's the difference. Okay. When we go with the DFS, the back edge is the edge going to the ancestor. But when we use the BFF with the cross F, we will check the node which is in the same level or in the next. So let's think about the graph BFS and BFS. You can take a look on the code. Okay. I give you the code for the graph. Okay. I took the code from the book, from the author. If you look at the code here, we have the class graph. So in the class of graph, we have vertex and we have x. So in the class vertex, we can construct. So we can construct and we can create the node. So it means we have an x, which is a node, and then we can mention or we can describe the element. What is the meaning by node? And yeah, this is to put the node into a kind of key. And we want to get what is the description of the node. If it is the x, then we can define what is the origin, what is the destination, and what is the element. So we have three, U, and X, destination, element. As you already learned before, we can find the endpoint. So the endpoint means if I have a vertex, so yeah, this is the endpoint from V1. So if I have this vertex, I have another, yeah, this is, let's say U, this is Z. Z is the endpoint of U. So the opposite, okay, so the opposite of V, okay, so it means we have, so the endpoint means we have the U and V at the same time, U and V at the same time. But if it is the opposite, I want to know what is the opposite of V, then the opposite of V is V. I want to know what is the opposite of U, the opposite of U is V, and so on, okay. So if it is a directed graph, we can change this into, if it is not directed or undirected, yeah, then become false. Okay, so the function we already learned before. So let's run it. Okay. Now I have one example of the graph. Let me show you. So in the graph, there will be some example. Check in some of you graph that problem. Now let's see that this graph shows a network of transportation among cities in Korea. So node represent the city. We have Seoul, Gwangju, Daejeon, Suwon, Busan. So let's say this is the Gwangju city. If you look at this one, you can see that this is directed graph. Okay. Why? There is a direction. Then yeah, it's represent X represent the availability of the transport. That means I can go from Seoul to Daejeon, but I cannot go from Daejeon to Seoul because the X is only one. I can go from Daejeon to Busan, but I can also go back from Busan to Daejeon. If I want to go to Seoul, I need to go to Suwon first and then go back to. This is based on X symbol. So X is shown as a diagonal. Then how can we represent it into the code? Let me use the X list. You should remember at okay. Before I mentioned to you the at this we have at list structure, and then we have adjacency list structure, and we have adjacency map. So these are the data structure for the graph. And as you learned already, they are different. Okay, different in terms of the performance. It means when you do with your thin project later, it depends on what are the data structure that you use. Now let's look at this ads list. In this ads list, I created this function, and let's make the initial value more directed to false. It means undirected graph. So I can include the graph. The graph is based on the selection of data. Check this one. So I will create the graph, and then for every V, I will input it. And then I will insert the vertex. For every E, there will be the source and destination. And then I can insert here. The first simple example, it is from the graph that I mentioned. Okay, so this is the graph that I mentioned to you here. So Seoul to Daejeon. So Seoul to Daejeon. Daejeon to Busan. Daejeon to Busan. And so Busan to Daejeon, Daejeon to Suwon, Suwon to Seoul, Seoul to Gwangju, Gwangju to Suwon, based on this graph. And this is the E. E is the tuple. How do you know tuple? A tuple use a list use square bracket. A set use curly bracket. Or dictionary also use the curly bracket. So this is a tuple. It means when you have this data, you cannot modify. So this is a directed graph. It means there is a direction from Seoul to Daejeon, there is a direction from Daejeon to Busan, there is a direction from Busan to Daejeon, and so we can click to the graph. Figure 14.3. So I will give you the figure. Okay. So this is the figure 14.3. So let's take a look. This is a graph network of airports in the United States. So the node represent the airport code. SFO is San Francisco, LAX is Los Angeles, and so on. X represent the route or trip of the airport without product. It means I do not know what is the X meaning, but I know that kind of no. This is another example in the chapter 14, figure 14.14. This is a graph with is a network of airports in the United States, and it's not representing the airport code. Now we have information about the X means the mile. So X represents the availability of the airplane on that airport, with the property mileage. So for example, if we go from San Francisco to Boston, then the mileage will be 2 and so on. So we can use this data and let's look at the code. For the figure 14.3, we can look at the graph before and then this is the source, this is destination, source, destination, source, destination. And then I want to create this into the graph by giving the information of E and then true. True means the graph. So that's the direction with each of the element. Now let's look at the graph Korea. So I want to use the simple example with this function. Then you can find what is the incoming x and outgoing x. So this is the exploration. I'm going to use the BFS. This is just for searching. Okay. So in the searching, I can look at the details. What is the incoming from one node and what is the outgoing from the node. So if I use the k comma v like this one, then it is a key and value. So in the key and value, it means you can look at the code here. It uses the dictionary. Okay. So in the insert text, okay. So when you want to get the outgoing or you want to get the incoming, so we are using dictionary. Then we can check the incoming items, which is K and V. I hope that you already know the dictionary. This is the content before the midterm. Respect again the material before the midterm. So I want to know what are the elements, and for every of the elements, I want to check. For example, Busan, there is an incoming from Daejeon. So this is the outgoing. In the outgoing, I can make the outgoing data into a dictionary. So I want to check what are the outgoing items. Then you can see the outgoing items from the graph that we already created. The next example is from the figure 14-3. From the figure 14-3, because it is only the graph, it is only to check the incoming and the outgoing. So the incoming from the 14-3, it is the same with the graph that I showed you before. It is the airport of this one. We can see the incoming. We can see what are the code from here. The incoming of JFK is Boston. The incoming of Boston is JFK. And we can also check the outgoing. Now you can look also at the figure 14-14. In the figure 14-14, you have the information of the x. The x means the mileage. So you can make the property like this one. SFO, San Francisco, to LAX. This is another node, Los Angeles. And the mileage is 337. SFO to Boston, the mileage is 2704, and so on. And we are going to put this x into the graph and then false. False means it is undirected. I run this, then I can create this figure. Okay. So again, you can check the incoming and the outgoing. So the incoming node, it will give you the information, what is the incoming, and also the mile information. Now let's check how if we use the BFS and how BFS. So this is the DFS from the chapter 14. So we already learned this one before. Okay. And let me just use the DFS to find the node, to find the exploration in the graph Korea. Okay. So we want to check the node. Okay. We just want to explore. We want to explore the graph Korea. So it means we can know that there are 5 nodes: Busan, Daejeon, Suwon, Seoul, Gwangju, and then we can find the incoming item. So yeah, this is based on the node that we already construct with the BFS. So if it is discovered, then we will find the node. So it is also the incoming from the graph 1. The graph 1 is the graph on figure 14-3. So we explore each of the node and we explore each of the end, whether it is discovered or not. So we just put all the discovered ends and discovered node. Discover incoming. Okay, so this is the result. And the graph 2 is using the figure 14.14. So I want to know what are the discovery edges from the graph 2. So this is the discovery edges from the graph 2, including the mine. This is the breadth cluster. Okay. I use the code from the author. I already show you this code. And using the BFS, this is also the same. I can use the graph Korea, and then I can see the result of exploration for every node. So this is the exploration, or this is the discovery engine. And then we have the graph 1. Yeah, we can run the BFS. This is the discovery engine. And this is the graph 2. And this is the discovery engine. Okay. In your team project, I ask you to make a small data. Okay. So for example, yeah, you can see this kind of graph. You can see this kind of graph, you can see this kind of graph, you can see this kind of graph, and then you can put into your code. Okay, so for example, I want to see like this data. So you don't need to use TXT1, you don't need to use Excel, just use the data structure in Python. So you can use list, you can use simple, you can use dictionary, just small data. Okay. And then I want to know whether your algorithm works or not. So in this case, because we are just using depth first and in the BFS breadth first, so we just get only the end. We just discover it. But your team project, yeah, it depends on the goal. So if you want to find the shortest path, it means at the end you need to show the path. If you use the sorting algorithm, then at the end you need to show the result of the sorting. And I also mentioned to you that you need to compare your. If your data is too small, you cannot compare the outcome on the time performance. So let me teach you how you can create data in random. This is an example. You can create the graph randomly. I use one library. The library name is network. This is already embedded in Python. So we can make a random. Let's suppose I want to make n equals to 10 and m equals to 30. So I can use the network X, and there is a function m random graph, and the graph will be created randomly. Now, if you look at this one, it will create a name, a file name, which is test at list. So you can see there is a file test at list. Then, yeah, this is the graph. This is the graph with 10 nodes. Yeah, the graph with 10 nodes and 30 edges. So this is 10 nodes and there are 30 edges. And then after you have this data, because it's random, yeah, you can perform the, and then you can check how long it will take to run with the big data. Let's say I want this is the iteration with one kind of data. I create a file, or you can create those data into a list. So every data will be inserted into this. So I create LL, it is an empty list, and then every edges it will be added into a file. As you know, the graph that I use is using tuple. So how to change from list to tuple? Then you need to convert with the tuple class. So the element, which is this, will be converted into tuple. After we have the tuple, this is the tuple, then you can run again the algorithm that you use before is the graph from at. What is yeah, this is the algorithm that I created before. This is the graph from at. So I have E is the collection of the edges. Okay, so E is the collection of the edges. So I'm using the element people, and let's assume that the graph is static graph. So true. And you already learned from chapter 3. We can calculate the runtime. In the runtime means I will check the starting time, I will run the algorithm, and then I will check the ending time. So I know how long the algorithm works. So I need to put it into one variable. Now I create another random variable n equals to 100 and I can also make another graph n equals to 1000, m equals to 3000. And let me check if I run this graph with the DFS. Then I will do the runtime performance. So this is the runtime. Now I will check if I run with the graph Fourier. If I run with the graph random 1, with random 2, with random 3. So let's check. If I run with the random 3, so this is the time performance. Now I increase again the number of nodes and edges. So I have the number 5. So it will show you long. Then yeah, you can just use very simple list. Put every of the time performance into a list, and then let's check the comparison. Now I want to check the performance between DFS and BFS. Then I also do the runtime for BFS. I do the runtime for every of the graph, random 1, random 2, random 3, random 4. And then I will do the span, and then I will check the X. At the end, I can show the result. This is the DFS. And then I can show the result between DFS and BFS. Okay. So at the end of the team project, you need to show like this one. What is the comparison between the in this case, I show the difference between DFS and BFS. Okay. I think that's all. Please check again this one for your team project. You can generate the data randomly just to show the runtime performance. Okay. Thank you very much for attending the class and see you next week.